have also this LHCb. Remember we discussed when we looked at discussed B physics, and this is one of the experiments at LHC, a study of B mesons. And one of the goals is also to check anomalies, which I have also mentioned before. Okay, today we will start some new topic, which is intermediate bosons. And I would call this also toward the standard model. We will again discuss this in the course of standard model, because various things related to intermediate bosons actually are related to features of the standard model. But still, to show how far we can go at our level reconstructing the standard model, I will discuss some new features related to intermediate bosons. So let me remind, we discussed four Thermian theory of weak interactions. And these interactions are described by Hamiltonian, effective Hamiltonian, which is G Fermi, square root of 2, and then product of the currents. And the currents are the sums of several terms, which include quarks and leptons. Now, I mentioned already that even Fermi saw that this is effective interaction, and at more fundamental level, there is exchange of intermediate bosons between two currents. To describe this process, you need to introduce now elementary couplings here of W boson with fermions, or with currents, and in this case the Hamiltonian is given by G 2 square root of 2, and then the product of two currents, on the product of the current, and the W boson. So that's the interaction, plus Hermitian conjugate. So this interaction is similar to what we have in electromagnetic case, where we have again current multiplied by the photon field, electromagnetic field. So here is the current is charged current, and therefore W boson should be charged particle. For instance, if here we have neutrino, which transforms into electron, and here we have D quark, which go to U quark at quark level, then W boson emitted in this direction should be W plus. So what are the properties of W boson? It should be massive. And this is because we do not see the structure at low energies. Otherwise, we would see long-range interactions like in the case of electromagnetic interactions. So it should be massive enough. It should be massive so much that maximal its mass should be bigger than maximal momentum, at which we see still point-like structure of the interaction. Now it should be charged, as I said. It should have spin 1. if you want to have analogy with electromagnetic interactions, right? So that's how it was introduced. And then these are currents, and once you have current, you have index mu, and therefore anything which couples with your current should also have index mu. So unavoidably we have here 4 index mu, and therefore W boson should have spin 1. Finally, interactions violate, they have V minus A structure, and therefore violate phi T. Now, having this more fundamental theory, we can give interpretation of what is G Fermi. So, what is this G Fermi? We can use comparison of the amplitudes computed with this Hamiltonian and with this one. In the case of 4 fermion interactions, the amplitude is proportional to GF square root of 2. In this case, instead of GF, we have this structure, which actually reduces to point here, to a single point. So, which means that the amplitude in the theory with W boson is given by G2 square root of 2 square of coupling, and then multiply by propagator of W boson. Again, I omit what is staying up. So usually what is staying is G mu. It depends also on the gauge which you use for computations. But it is enough to take G mu nu, and therefore you will have just one here to compare with. Okay? So if you are at low energies, that is Q squared much smaller than MW boson squared, then we can rewrite this as G2 square root of 2 squared 1 over MW boson squared. And I will omit sign. Sign doesn't matter here. So, which means immediately that G Fermi square root of 2 is this quantity. Let me write it probably here. So, now we can write that GF square root of 2 equals G squared 8 mass of the W boson square. Okay? So, let me remind that Fermi was kind of so deep in this type of analogy with electromagnetic interactions that he suggested that probably G equals E, electric charge. Using this equation, and since we know what is G Fermi, you can find what is the mass of the W boson. And Fermi estimated that under the only what is not known is this, right? G. This you measure, G Fermi, from just rates of beta decay. So this Fermi assumed to be equal E. And therefore, the only unknown is mass of the W boson, and I will not resolve this as a simple equation, of course. What Fermi got is that the mass of the W boson should be something like 37 GeVs. In the standard model, this is not true, actually. And in the standard model, G is given by E divided by sine theta weak. And theta weak is weak mixing angle. So in what follows, you will see more and more mixing. Actually, the general rule is the following. M everything what can mix, mix. And if something is not mixing, then most probably there's a good reason for this. It's the same as everything which can decay should decay. This problem is kind of related to generalized increase of entropy, if you want, you know. So everything is kind of converges to some kinetic or motion, to like in the case of decay, or to some mixture, and you know, eventually one expects to have something which is completely mixed. Anyway, so this is the mixing angle. I will say a few words a little bit later. And that was measured, and the measured value of this sine theta is 0.47, I think. Yeah. So this is 0.47. I remember that sine squared theta w is 0.22. Actually, it's like a square root of Kabiba angle. So one can remember also this thing. So therefore, G is bigger than electromagnetic coupling constant, and I will not discuss this. You will learn from the standard model. So what I want to say is that G is bigger than electric charge, and therefore true mass of the double boson is bigger. And what we have now is the mass of the double boson is, let me say precisely, is 80.38 GeVs. And I'm giving you a complete number, because when you do this just using this computation, you will find something like 78 GeVs. And then you need to take into account radiative corrections, which actually increase the mass of the W boson. So it's 80 GeVs approximately. Okay? I don't want to delete this because I will need this. Maybe I will delete this. And so let's come back. W bosons couple with currents, and that is depicted in this way. So we have W boson and fermions. And what are these fermions? So W can transform electron to electron neutrino, and that will be W minus if it propagates in this way. Muon, mu, and others. So it can be D and U. And all the currents which we have discussed, or in other words, all the doublets of fermions we discussed have this coupling. And this coupling is universal. So it is the same for all currents. I have deleted here Lagrangian, but you saw that it is proportional to the same coupling constant. Apart from mixing, of course. If you do specific transitions of quarks, then you need to take into account, of course, mixing. But all the doublets with mixture, so we have U for in the quark sector, D CKM, we introduce this. We have charm, and then this is S CKM, top D CKM, which are mixtures of U. So all these pairs have the same coupling, which is G2 square root of 2. It's universal. So W boson has these universal couplings. Questions? Well, I should probably add that the width or decay rate of total W boson is around 2 GeVs. I have some precise number here. You can say so 2.085 GeVs. So it's 40 times smaller than the mass itself. But 2 GeVs, if you transfer this into lifetime, then you will get something like 10 to the minus 25 seconds. So it's very quickly decaying particle. Very quickly decaying particle. Okay? Now, so I don't know, let's see. Now let me discuss minification. This is a great idea and great heuristic principle of development of physics and development of theory. In this way, we unified electric and magnetic phenomena, for instance. Here we deal with electromagnetic phenomena and weak interactions, and the idea is to somehow unify weak interactions and electromagnetic interactions. So can we unify these interactions? Unification to somehow implies analogy or similarity, because you cannot unify things which are completely different. So it should be some similarity of things which you try to unify, like we unified hadrons in families. And this is because they had some common properties. Now we want to unify weak interactions and electromagnetic interactions. Mediators of weak interactions are W plus, W minus, and here we have gamma. When you unify something in particle physics, this means that you want to consider this particle with 3 as having the same origin. Or, in other words, they kind of different states of the same particle. So we are reducing 3 different particles, to just a single particle, and say that there are different states of this single particle. In the same way as we unify proton and neutron in the doublet, saying, oh, this is the same, this is just the same particle, but 2 different states of nucleon. Similar ideas behind this. So, and that has been discussed already in 50s. So, can we somehow, starting from 50s, can we really do this unification? So, unification implies that instead of different couplings, you introduce single coupling. And instead of different particles, you introduce one particle. Or put them in one multiplet. So, in more kind of formal thing, the question is, can we put these particles in the single multiplet? So, do they form triplet? Like W plus, gamma, W minus. In the same way as we have written isospin, triplet of pions. Remember, we have this isospin triplet. So this is the whole idea behind. So we know that SU2 group, which is the simplest unitary spatial group, which has triplet representation. So it has triplet representation, and this is a joint representation, yes, of SU2. So the question is, can W plus minus and gamma form the triplet or a joint representation of SU2? Again, what is behind this unification is that the theory of weak and electromagnetic interactions have certain symmetry, SU2. So this is what we are trying. And W gamma and W minus form the triplet, which transform under triplet representation of SU2. And the theory is somehow invariant under these transformations. So, now we can try to write Lagrangian or Hamiltonian of weak and electromagnetic interactions in the form G2 square root of 2. I don't want to put it here, so G, then I have over 2 L gamma mu W matrix, and I will explain what is this matrix, L plus Hermitian conjugate. Now, L is the doublet. So let me just take electronic doublet. Electromagnetic neutrino, and the same should be done for all other doublets in the theory. And then W matrix is the following. It's W0 over 2, W plus square root of 2, W minus square root of 2, minus W0 over 2. Over 2. So, these are W plus and W minus. So this is neutral component of the triplet, so I'm considering the triplet W plus W0, W minus. Before I will introduce photon in this, so there's this neutral component. And this is the matrix. You see, all diagonal elements of this matrix, they give transition between nu and E, and in this way I will reproduce our usual charge currents. So please check this. We just multiply this matrix onto two columns. This is line, this is column. And at least you will reproduce correct interactions of W plus and W minus. Okay? So this is coupling constant, and so that this is the W. Clear? So insert L and W hat matrices, multiply, and then you will get correct at least charge current interactions. Now the question is, can we identify WZ? By the way, so let me, before I will continue with this, let me say that by that time already Yang-Mills theory has been developed, how to construct invariant Lagrangians for non-abelian group, because here we are discussing SU2, which is non-abelian symmetry group. And actually this structure appears as sigma matrix multiplied by I, and this is sigma W, and is W1, W2, W3. And then when you multiply sigma power matrices, you will get the structure. By the way, this W plus will be related to W1 plus I W2, and W minus is conjugate. But for us it is enough that we are introducing this matrix. You can check that it works. So this is the way how SU2 symmetric interaction is constructed. And you can check actually that this structure is SU2 symmetric. By the way, this is completely the same what we have discussed due to tutorial when we discussed, remember, interactions of proton and neutron, nucleons, with pi zeros. So this is analogy of pi 0, pi plus, pi minus. And remember, we represented triplet in this form, precisely. And it was pi 0, pi plus, and pi minus. And that form was SU2 invariant. This is precisely the same. Okay? So which means that this is SU2 invariant. Doublet, and this is triplet. So in this SU2 symmetry, L is transformed as a doublet representation of SU2. By the way, this is very similar to isospin. And for this reason, this symmetry is called weak isospin. So we are talking here about weak isospin. And also we are talking about weak hypercharge. In contrast to this hadron structure, So we introduce all isospin only for proton and neutron, or U and D quark. Here we introduce weak isospin for all doublets. We discussed already. Okay? Now, the question is, can we identify W with photon? That would be nice, right? So if you say, okay, W, 0 is photon. Unfortunately, no. For several reasons. There are several problems, actually 3. The first one, this W couples with neutrinos, and photon shouldn't. So the problem is electric charge. Because W will have coupling neutrino, for instance, neutrino and double 0, right? It's just here neutrino, neutrino, and here is double 0. It should not be for photon. The second problem is V minus A structure of weak interactions. I haven't written here. However, remember, to have correct weak interaction, I should insert here 1 minus gamma 5. This is what we can discuss always. To have V minus A structure of W interactions. But then we will have also V minus A for W0. It shouldn't be for photon. Photon should not violate parity, and the coupling should be without this factor. So this is the second problem. And the third problem that you see, gamma is massless. While W0 should be massive, because we haven't observed any neutral gauge bosons apart from photon that time. So it should be massive. Now, how we resolve this problem? And actually there were several possibilities, and it was a big model building, especially in 80s or 70s, before everything was checked. So what is the solution? You need to extend the theory. Not just use doublets and the triplet adjoint representation of SU2, but you need to either introduce new fermions and consider not doublets of fermions but triplets. That was very nice model by Georgia and Gleshow based on the triplets of fermions. So you need to introduce some new particles, new fermions. Or you need to extend the theory by introducing new bosons, new gauge bosons. And actually this possibility won eventually. That was excluded. And it was excluded by observations of so-called neutral currents, which I will mention a little bit. So, the solution was proposed by Gleshow and Ward. There are a few papers, but Sheldon Gleshow got the Nobel Prize for this actually. And he extended the theory by SU2 multiplied to U1 gauge group. So he added one additional gauge boson. Let me denote it by B0. So this B0 corresponds to U1. And here we have these three W bosons, plus, minus, and 0. Okay? So let me give you just outcome of this construction, because you will study this in the summit model course. But already you may have some idea what is really working here. This B0 couples not only with doublets, but also, which are left-handed, but also with right-handed components. With left-handed and right-handed thermians. And right-handed thermions are singlets under SU2. So we introduced doublets, right? We have neutrino and electron. And those are left-handed components, because we have this 1 minus gamma 5, and this 1 minus gamma 5 pick up only left-handed components, and right-handed do not participate in the interactions. So right-handed components have no interactions with W boson. Now, so these are left-handed, but also right-handed components. So, of course, right-handed components of electrons should exist. And this B0 interacts both with doublets and with right-handed singlets. Now, this is the first step. Well, B0 can be in the first approximation like a photon, you know. So photon has this U1, but not completely, because B also should interact with doublets. Photon turns out to be mixture of W0 from triplet and B0. So gamma equals cosine theta W, and this is where the weak mixing angle appears. So gamma is cosine theta weak B plus sine theta weak W0. Orthogonal combination to this, we denoted Z0, and this is just orthogonal combination of B and W0. So it will be sine here cosine W0 minus sine B. Now, the trick is that using couplings and theta weak, we can arrange the things that photon introduced in this way doesn't couple with neutrinos. So you have no problem with electric charge. And it has equal coupling with left and right-handed components, so that the parity is conserved. So, with solving this problem, electric charge, correct electric charge assignment, and B structure of electromagnetic interactions, of gamma interactions. Now, last problem is that we have photon, which should be massless, and W0, which is massive. That indicates that symmetry should be broken. So SU2 cross U1, SU2 cross U1 should be broken. In the limit of exact symmetry, all the masses of components of your multiplet should be the same. And not only this, gauge symmetry tells us if this is gauge symmetry, and it should be because W and gamma enters the same triplet. Gamma is gauge boson, and therefore W plus W minus are also gauge bosons. In the limit of exact SU2 cross U1, gauge symmetry, everybody should be massless. Now, the fact that Z has mass tells us that the symmetry is broken. And in fact, this SU2 cross U1 is broken to U1. And this unbroken U1 is kind of mixture of this U1 and this SU2 boson. So in this way, we solve all the problems for unification. So we introduce Z0 as mixture of W0 from triplet and B from singlet. So this U1 gauge boson. And symmetry breaking, and for this Higgs mechanism was used. This I will not touch even, which gives the mass Z0, but not the mass of photon. Questions? That is it. Wait, some questions?
I have a question.
Yeah.
So this B boson and the Z boson, W boson are not the same thing. Like how are they different?
So you see, this is mixture. Z0, probably I should say the following. They have different properties, yeah. So we have W0 and we have B. So these particles have definite symmetry properties. Z0 and gamma are states with definite masses. They have definite masses. So gamma has 0 mass, and this has mass. We will discuss what is this. So in the mixture again, when you have incoincidence of states with definite symmetry properties or definite weak interactions. So this guy has SU2. This is from SU2. This one from U1. Actually, here we also introduce weak hypercharge, not only isospin, but hypercharge, which actually gives the couplings with U1 symmetry. So W0 has weak isospin 1 because it enters triplet. B0 has weak isospin 0, so that's singlet. So W0 has the third component of weak isospin 0. Okay? So these guys have definite symmetry properties, weak isospin properties. Those have definite masses. And mixing is when we mix particles with different properties. So photon has a component with non-trivial isospin and isospin 0. And the same is Z0, they are orthogonal combinations. Now the masses of Z0 so let me now discuss a little bit properties of Z0. So you see, the reduction of Z boson is outcome of attempt to unify weak and electromagnetic interactions. It's not completely satisfactory unification, because still we have this, not just a single group, SU2, but we have SU2 cross U1. Each of these groups have its own coupling constant, so that we are not really unifying, say, electric charge or electromagnetic coupling constant and weak coupling constant. So we are just reshuffling, so instead of electric charge and G, so originally it's G and G prime. G prime corresponds to U1. So we start with two couplings and we end up with two couplings, and so there is no unification of couplings. And even it's not kind of very good unification of gauge bosons. We can get very good unification of everything in grand unification, SU5 theory. But this is a separate question, of course, with this SU5. So properties of Z0, so it's massive, and the mass of Z0 is given by the mass of the W boson over cosine theta weak. So this is very important parameter, this weak mixing angle. It enters in many places, and in particular here in the relation between masses. So MZ is heavier than MW, and the mass of Z boson is 91.19, so it's kind of inverse thing. GeVs. Remember, W boson has mass 80 GeVs. The width of Z boson is 2.5 GeVs, even slightly bigger. So couplings of Z0 are not universal as W. So they're different from for upper components and doublets. So you have doublets, upper and down. So let me put that upper component and this down component. So they differ for upper and down components. And also they differ from for left and right components of fermions. So there is no such universality as in the case of doublet. Now, so the coupling is of the form fermion, go to fermion, and then Z0. And actually, it couples with all the quarks and leptons. Okay? What is important that this is flavor conserving currents. Which couple with Z0. And this is important, right? So we had this problem with flavor changing neutral currents. At least in this model, automatically Z0 has flavor diagonal coupling. So a given fermion is transformed to the same fermion. Of course, we still have a problem when we have loops. So when we compute loops due to charge currents, in fact, that's what we have discussed. But at least in the lowest order, you have no problem with flavor changing neutral currents. This is not the case when you start to extend the standard model. So nowadays, theorists try to extend the standard model, introducing some more stuff, and then that is hit by this flavor changing neutral current problem. You should be worried about if you don't violate existing bounds. At lower energies, so we have the situation with exchange of Z0, F, F, and here F prime and F prime. This is reduced to point-like interactions, as in the case of charge currents, F prime. So we'll have here 4 fermion interactions at lower energies. And this is similar to what we had originally. And that is described by the product of currents, now neutral currents. So I can put here neutral currents, and here mu, and this neutral currents, mu. So, but the couplings are not universal. I cannot write a single G Fermi like in the case of charge currents. Questions?
I have a quick question. So when you wrote the photon field gamma, you really meant the 4-vector potential A mu, right?
Yeah.
And I have another question. So the fields of the other bosons like Z bosons and the W, they also have the vector index, right?
Yeah.
And when we write the Lagrangian, the lepton and gamma mu, and then the matrix, 2x2 matrix of W, inside the W, it has the vector index.
Oh, sorry, I just missed this. Yes, sure, absolutely. So, because I was kind of focused. So all these 4 fields staying in the matrix, they should have index mu, which actually connected to gamma mu. Yeah, please add in your notes. Sure, yeah. So all they are 4 vector fields.
Okay, thank you.
More questions? Well, there is nothing complicated. We actually almost done the standard model within this half an hour, because that is to a large extent, apart from Higgs part, so there's still Higgs mechanism should be added to give the masses. I haven't discussed how W boson and also other fermions get the masses. But this is really true core of the standard model. I don't want to enter this. This is just to have a connection to what you will hear in the second semester. But we are almost, done with the standard model. So, of course, some new element is this mixing, right? Angle, weak mixing angle, which is non-trivial. And now let me discuss how this mixing angle has been measured and how things were established. So, one of the predictions of the standard model is existence of neutral current interactions, right, of this type. And so you expect these neutral current processes. And I will discuss discovery of neutral currents. Very briefly. Now we will move very briefly, because that will be repeated from, I assume, in the course of standard model. So neutral current discovered. So discovery has been done in 1973 at CERN. What has been discovered is the process of muon neutrino scattering on electrons. And also antineutrino, antineutrino plus electrons, anti-muon neutrino plus electrons. For this discovery, experimentalists used the bubble chamber with the name Gargamel. Invented by Glasser. So this chamber used again phase transitions to visualize tracks, but here it was phase transitions of a liquid gas. So the tracks were visualized by bubbles of gas, which are produced when particle crosses the chamber, ionizes medium, and then phase transition of liquid to gas occurs. This is inverse what we had discussed before. It was gas to liquid. Now there's liquid to gas. And so the phase transition occurs as small bubbles along the track. Then you make the picture, and then you see the track. So what has been seen, actually this chamber is staying, if some of you will be at CERN, you can see this chamber. It's like an exhibition, so outside of laboratory, so it's just on the open space, this chamber is staying, and also some other devices. So you can, that's like this size. Actually, I have the picture. So this is the picture of Gargamel, and so that's how it was inside, but when it was working, so it was of course in the experimental hall, but now it is staying here. You see the tree here. you can, and the size is, I think the person is staying here. If you see the person is staying here, it's maybe just like that. So that's this chamber, bubble chamber. Okay? And so what they saw in this bubble chamber, the tracks, which you see here, it just, just like this, some simple track. So what they saw are events of the type like this. It was also magnetic field. So, but then they saw the tracks with bending tracks, and so that was direction to acceleration. So this track has been identified with the track of electron, recoil electron. So you see in these processes you have electron recoil, right? This is at rest more or less, then neutrinos were in GeV range, quite energetic, and so they produced recoil electrons with this energy, and experimentalists saw the tracks. Well, I'm always kind of amazed that, frankly, I cannot say where it's precise, but I think this is the track of electron, although there are some additional tracks here. How experimentalists can immediately identify something interesting. So I looked at various plots of this type, and I was much more interested in something which they are considering as a garbage, and they say, oh, that's important, but this is garbage. So one needs to have some training to really recognize what's going on. Okay? So that was great discovery, actually. It's amazing that they didn't get Nobel Prize. This is the first confirmation of the standard model. So since neutral currents exist, then Z0 exists, then all the models which are based on additional fermions were immediately rejected. Right? So I said that it was very nice economic model with triplets, but without Z boson. So that was everything. This has been rejected. Next discovery, which I want to discuss very briefly, or maybe you can ask questions. And this was the very significant step in confirmation of the standard model. That was prediction of the standard model, and this discovery in 1973 was a very important step. After this, people almost started to believe that standard model is true model of electroweak interactions. And now we are calling these electroweak interactions, not just electromagnetic and weak interactions, because this is somehow unified model, not more, maybe perfectly, but unified model. So next discovery is discovery of W boson, W and Z. Oh, I probably should add, the rate of these processes depends on weak mixing angle, and depends on theta W. And therefore, measuring the rates or cross-sections of this process, you can define what is theta. So, theta V was known after discovery of neutral currents. So it's interesting that they discovered this in scattering on electrons, but of course neutral currents exist and observed later in scattering of neutrinos on nucleons. But this is a clean process because you have just one electron, that's it, going out of nothing. So you have nothing here and then electron is being projected. Now, discovery of W boson. Once you know what is theta, remember you can predict what is the mass of W and Z. So planning experiment, experimentalists already knew what should be the mass of W boson and Z. So that was kind of planned discovery. Everything was known. So the experiment has been done again at CERN. And they used synchrotron with the name SPS. Actually it works now, it works as pre-acceleration for LHC. In this experiment they collided proton and antiproton with the energy 270 GeVs each beam. So protons and protons, it was symmetric collider. Protons and antiprotons were accelerated, and each beam had energy 270 GeVs. There were two experiments, UA1 and UA2. And it was an interesting story actually, how they competed with each other. And Carlo Rubbia, who got the Nobel Prize for this discovery, was in UA1 experiment. So what was the process? W bosons were produced when you collide proton and antiproton, and you take U quark, for instance, from proton, and the antiquark from antiproton. They can annihilate in W plus. So actually you have an exercise playing a little bit with this, right? So you have this current, right, when U is transformed to D and W is emitted. Now W plus can then decay in various modes, and in particular into positron and neutrino. And also they can decay into mu plus and mu. And they can also decay in all other pairs of quarks which W boson couples to. In all pairs of fermions we have discussed, apart from, of course, top quark is heavy, so W boson cannot decay into top quark. So, what has been measured is the following. This channel was used when you have electron or positron and neutrino, and only electron has been observed, right? Neutrino just escapes. So you have the following signal. You collide proton and antiproton, and at so big energies, proton and antiproton can be considered as the fluxes of quarks or partons, as we discussed. So you have just two beams of quarks and antiquarks, and they collide. So everything can be considered just at the level of the quarks. So it was this collision, then quark antiquark annihilate, and you have many secondary particles, the energies are quite big, and just one electron or positron, like in this process, with big transverse momentum. So we are saying that momentum, which is orthogonal to direction of collision, this is transverse momentum, Pt. Okay? And the energy of this positron can be 20, 30 GeVs, so they establish in the threshold. So selected events when you clearly see the track of the electron, which actually emerges from a big number of hadrons as secondary particles. So they measure the distribution of these events, they observed many, number of events with this big PT as a function of transverse momentum. That look like this. And also you see this imbalance. In the first place you see that there is some momentum in this direction, but there is nothing here, which clearly should be identified to neutrino, which is moving in this direction. So that's important signature, as we are saying, of these events. So they measured this distribution. The first computed, of course, measure, and this peak is more or less corresponds to half of the mass of the W boson. So it's not a peak, it's kind of, the curve is maximum, MW over 2. So we could see the peak if you would detect neutrinos and measure the momentum of neutrino. So this is as far as W boson is concerned. Actually, they measured also this angular distribution, and eventually everything was fine. By the way, yeah, I will show you this maybe. So that's, you see, Carlo Rubbia celebrating discovery of W boson, and this is another plot. You have this, and you see this messy secondary particles system, and one track here, which corresponds to electron or positron. Okay, just open this. I hope you have this. So just this track. So this is production of W boson. Now Z boson is to some extent simpler. Z boson, again the same process. We have proton plus antiproton, Z0 produced plus the rest, and then that zero decays into E plus and minus. It also decays into mu plus and minus and other modes, but these are modes which are very convenient to make these studies. What they measured in this experiment, invariant mass of E plus, E minus. So what measurement is? Measurement of invariant mass of E plus, E minus. And you can now understand well, so they saw something like this. Background and the peak. On the top of the background, so this is invariant mass of E plus and minus, that's the number of events, and they saw this peak, and the peak is quite wide, it's 2 GeVs, 2 and 5 GeVs, so they can even measure, actually, to see what is the width of this peak, and that was in the range 90 GeVs, where it was expected, and that was identified with the peak due to Z boson production, and Z. So later, lab experiment which is electron-positron collider in the same ring as LHC is running now. Lab experiment, so that was E plus and minus collider. And they preferred very precise measurements of this Z0 peak. If you see the plots, the point is like this. So they really see that Z0 has no definite mass, so there is a distribution in the mass. So that's the They measured this gamma, and this gamma actually has two components. One is visible, and another is invisible. And invisible is due to decay of Z0 into neutrino, antineutrino. So the peak for any mode, E plus, E minus, mu plus, mu minus, it has the same width. Remember, it's total width. So the total width, what gives you the width of the peak. Now you can measure or determine this by just, counting, making computation essentially. The rate of particular, so you can measure the rates of particular decays. And then subtract from total rate, and you can find out what is this invisible decay rate due to neutrinos. That allows you to measure how many neutrinos exist in nature, right? Because this invisible is given by gamma of single neutrino multiplied by the number of neutrino species. And it was established that this is in very good agreement with 3 neutrinos. By the way, recently it was some update also using LHC data, because before it was that this n effective was a little bit smaller than 3, and people said maybe there's some new physics behind this. But eventually it was established, quite recently by the way, that it's in perfect agreement with 3, which means, it's a very important result, that we have 3 generations of fermions, it looks, at least normal, with light neutrinos. 3 generations of charged leptons, 3 generations of quarks. So everything is just in 3 generations. Questions? It's not alphabets. There are a few more discoveries. We haven't discussed discovery of top quark and tau neutrino. These are kind of final discoveries, and also Higgs boson, right? So what is left actually to discuss is Higgs boson, discovery of tau neutrino, and discovery of top quark. I will do this a little bit later. What I want to start today is start this part related to symmetries. So next lectures will be devoted to symmetry in particle physics. I gave already some introduction, and again let me remind, I have discussed this situation with just circle. Circle is symmetric, it has certain symmetry. It has symmetry with respect to rotations and also reflections, which means that you are doing transformations and nothing is changing. Maybe I should add also, this is exact symmetry, however the symmetries, and we will discuss symmetries which are broken also. If you will have not a circle, but you will have ellipse, suppose you have the figure, which is ellipse. Ellipses also has certain symmetries. You can make reflection in this way, but it has no rotational symmetry. So you have x squared plus y squared, which is ideal circle, but you can say, okay, maybe here is something like not 1 but a, and a is not equal 1. So that is breaking of the symmetry. So you can, if you can make this kind of corrections, you will, this means that you are breaking the symmetry, so you can write this as x squared plus y squared plus a minus 1 x squared, and then we are saying that this term violates the symmetry, right? Sometimes this violation symmetry is very small, and then we are saying the symmetry is good, right? It's not although not exact, but not precise. So, actually all the physics can be formulated in terms of exact symmetries and violation of the symmetries, in principle. mostly we will discuss the symmetries of Lagrangian. Maybe I will write this later. So, as we discussed invariance, of the symmetry, symmetry is invariance under certain transformations. Again, remember this symmetry is invariance under certain transformations. And therefore, to define symmetry, you need to define transformations. So, remember this. Actually, what we will talk about the symmetries of Lagrangians or Hamiltonian. We also will talk about the symmetries of states and symmetries of equations of motion. Okay? So let us first discuss symmetries of the Lagrangian or Hamiltonian. So in this part, but this is the same, right? So in Lagrangian you have a kinetic term, a minus potential. So in Hamiltonian it's plus, the same. So in general Lagrangian is some functional of coordinates and fields. So we can define transformations if you want to explore the symmetry properties of Lagrangian, which are transformations of fields, coordinates, and transformations of fields. So we need to define this, which means that we need to introduce relations or connections between starting variables and transforming. So in general, to define the transformations means that we define relation between, say, starting field and transformed. And the same for coordinates, x. And g is some functional, it's just a schematic, so it may be just simple relation, maybe just a change of the sign. But in general, we need to introduce law of transformation. You can call this the law of transformation. How original coordinates are related to transformed coordinates, or vice versa, you can of course resolve it. So, once you introduce this, you can check invariance of your Lagrangian. So what are you doing? You are inserting here this f and x in terms of f prime and x prime. And you will get Lagrangian gf f prime gx x prime. And we are saying that Lagrangian is invariant under G transformations if we can reduce these to G F prime and X prime. That is to the same form of Lagrangian, but in these new variables. So we have discussed, this is the same, you can check again with this circle plane. So the form of Lagrangian should be the same. It should not be changed under these transformations. Then we say that G is the symmetry transformation. So Lagrangian is invariant. So if this equality exists, then L is invariant under G transformations. So, if we observe that Lagrangian is invariant, then we can find out consequences of invariance or consequences of the symmetries. Let me write it here. So, consequences. Actually, a given Lagrangian may have different symmetries, several symmetries. The consequences or physical consequences of the symmetries depend on the type of the symmetry. So different symmetries have different consequences. By the way, the game is in two sides. So you can have already some Lagrangian found from experimental data, constructed Lagrangian, and then study symmetry properties of this Lagrangian. You can do the opposite way. So you can define some symmetry and say, I want to construct Lagrangian which is invariant under the symmetry. So people are working in both directions. You can introduce some symmetry and then construct Lagrangian and then see what are the consequences. Or you can study the symmetry of already known Lagrangian. What are these symmetries? What are these consequences in general? So, consequences. Of symmetries. Symmetry provides classification of particles. You might already do this, right? So we have this SU3 flavor symmetry, and the SU3 has the generators which correspond to isospin, operator of isospin and strangeness. And so using this symmetry we can classify particles according to strangeness and isospin. This is one example. Another consequence is conservation law. And also selection rules, certain selection rules. For processes. So, like baryon number, we have or lepton number, we have certain symmetry, and as a consequence of this symmetry, we see conservation of baryon number or lepton number. Some other characteristics. As a consequence of symmetry, we have conservation of electric charge. Another consequence possible is equalities or relations of masses of particles. So, in the case of exact symmetry, we expect equality of masses of particles which enter the same multiplet. Doublet or triplet discussed. So next, the symmetry actually leads to certain properties of amplitudes. Of amplitudes of processes. Now, some dependencies of your amplitudes can be ruled by the symmetries. And finally, which is very important and powerful thing, symmetries give relations between probabilities of different processes. Extremely important property of the symmetries, and this means that it simplifies our life. So it's enough to compute the probability of one process, one reaction. And then using symmetry, you can find the probabilities for many other processes. Then I will illustrate it properly in this picture. Let me start topic, which actually I will continue. I just started next lecture. This is symmetry at quantum level. So mostly we have discussed symmetry at classical level, right? For time being. Actually, at quantum level, many things become even more simple if you are acquainted with this. Let me think, symmetry. So, in quantum field theory, or theory with second quantization, everything becomes operators. That is, we introduce physical quantities. Which are operators, right? For each physical quantity we introduce operator. And also we can construct states using operators. Or fields. Fields are operators, let me put here fields in the first place. Physical quantities, fields. So everything can be expressed in terms of operators of production and annihilation. Everything. And so once we know what are commutation relations between them, then we can proceed with computations of different quantities. So we have field operators. Now our fields are operators. We can construct now states using the vacuum state, introduce vacuum state. And then arbitrary state can be constructed as action of operator F plus onto Viking state. What is important that even symmetry transformations become operators. So what we have introduced this G, and let me write it explicitly, that transformations also become operators. So we introduced operators of transformations. Our G, what we have discussed, now become operator. So in fact, these transformation operators can be expressed in terms of field operators. So not only they are becoming operators, but they can be expressed in terms of field operators, or again in terms of annihilation and production creation operators. Everything becomes the operators. Probably the last thing which I want to tell you is the following. Suppose we have operator O. Then transformation of operator, and we have transformation U. So U is the operator of transformation. Then this operator is transformed in the following way. Transformed is given by U O and U minus 1. So U minus 1 is inverse transformation. So U minus 1, U minus 1, U is unit. In fact, this way to introduce transformation properties matches what we have at classical level. So it's not accidental. So remember, at classical level we have just something which, some field, and transformed is this field multiplied just once, multiplied by symmetry transformation. Here we need to put symmetry transformation. These are also operators. In this place, in front and the back of this operator. So this is the transformation property. In particular, if you have field F, then it transforms as U, F, U minus 1. So this is the transformation law of the field. Of field operator. And very often we will just use unitary transformations. For unitary transformations, we have U diagonal equals 1. Or U minus 1 equals U diagonal. so that's it for today, and we will continue with the symmetries later. I probably will show you some more pictures in the end. So this is discovery of Z boson. I probably should show this before. You see again, this is UA2 actually detector, and here you see many secondary hadrons, and then 2 tracks long, which corresponds to, say, E plus and minus, I think, produced from Z0 decay. And so they are not along the same line because Z0 moved, and therefore they are not back to back. And so they measured the energies and momenta of this electron and positron and found what is the mass of Z0. Let me see if I have some other plots. So that's UA1 and UA2 detectors. Sorry, I didn't show this. So this is UA1 and UA2 detectors where W and Z have been discovered. And I think you can find some person here staying. So that's already a couple of meters, if not more. So I think it's no. So the person is staying here. No, you can see. I think it was. Oh, the person is staying here. So that's a few meters long. So these are U1 and U2 detectors to discover Z boson and W boson. Questions? Sorry, I just forgot to show. So that's the beginning of symmetry topic. Questions?